So now I would like to explain about the basic definitions on Biot Savart's law. First one is magnetic flux. The lines of force around a magnet is called a magnetic flux. It is represented by pi, units are Webers. 10 to the power of 7 magnetic lines equals to 1 Weber of magnetic flux. So generally every magnet having its field. So around the magnet up to some region, its effect is exist. This region is called magnetic field. Magnetic field is nothing but a combination of magnetic flux lines. 10 to the power of 7 magnetic flux lines equals to 1 Weber of flux. So next one is magnetic flux density. The magnetic flux per unit area is called magnetic flux density. It is a vector quantity and it is represented by B bar. B bar equals to magnetic flux by area. Units are Webers per meter square or Tesla. So in electric fields, electric flux density is there. In magnetic fields, magnetic flux density is there. So electric flux density represented by capital T bar, magnetic flux density is represented by capital B bar. So next one is magnetomotive force. Magnetomotive force equals to N into I. Here N is number of turns of the coil, I is the current flowing through the coil. So units are ampere turns. The magnetomotive force, so which circulates the magnetic flux in magnetic circuit. In electric fields, similar parameter is electromotive force EMF. EMF circulates the electric current in a circuit. So similarly in magnetic fields, the magnetomotive force which circulates the electric flux in a magnetic circuit. Next one is magnetic field intensity. So the magnetomotive force per unit length is called magnetic field intensity. The magnetomotive force per unit length is called magnetic field intensity. It is also called as magnetic field strength. It is a vector quantity and it is represented by H bar. H bar equals to magnetomotive force by length. Units are magnetomotive force. Units are ampere turns. Length units meters. So magnetic field intensity units are ampere turns per meters. In electric fields, similar parameter is electric field intensity. It is represented by E bar. E bar equals to electromotive force per unit length. So next one, the relation between the magnetic flux density B bar and the magnetic field intensity H bar. It equals to B bar equals to mu into H bar. Here B bar is magnetic flux density, H bar is magnetic field intensity, mu is permeability. Mu equals to mu naught into mu r. Mu r is relative permeability, mu naught is permeability in free space. So mu naught equals to 4.2 10 to the power of minus 7 henries per meter. It is constant value, and mu r relative permeability value always depends on type of medium. It depends on type of medium in which the magnet is present. So permeability equals to mu naught into mu r. In electric fields, similar parameter is electrical permittivity epsilon. Epsilon equals to epsilon naught into epsilon r. So similarly, it is a magnetic permeability. So next one is Biot Savart's law. So first, by using Biot Savart's law, we can find the magnetic field intensity and magnetic flux density. The purpose of the Biot Savart's law is to find the magnetic field intensity and the magnetic flux density. So it gives the relation between current and the magnetic field. So in 1827, scientist Ørsted discovered the current carrying conductor produces the magnetic field. So we know that the current carrying conductor produces the magnetic field, but it is first discovered by scientist named Ørsted in 1827. So before that, by using permanent magnets only, we are producing magnetic fields. After 1827 only, electromagnets are exist. So the source of magnetic field is moving charges or electric current. It means if charge is moving, automatically the magnetic field is produced around the charges. So moving charges means current. If a current flowing through the conductor, it means the charges are flowing in the conductor. In that situation, around the conductor, the magnetic field produced. So by using Biot Savart's law, we can find the magnetic field corresponding to electric current. So previously we said that the current carrying conductor produces the magnetic field, but for how much of current, how much magnetic field we can produce, so we can determine by using Biot Savart's law. So by using Biot Savart's law, we can find the magnetic field or magnetic field intensity corresponding to electric current. So now let us consider one current carrying conductor. This is conductor. In this conductor, current equals to I. Next, let a point P at which the magnetic field intensity is to be measured. So let a differential length of the conductor dl. dl is differential length of the conductor, and this differential length to point P, distance vector is r bar. So current element means current into differential length of the conductor is called current element. So current element equals to I into dl. I is current, dl is differential length. So current element definition, the product of current into differential length of the conductor is called current element. So mathematically I into dl is current element. So here, so first we find the magnetic field intensity at point P due to current element. It means we are determining the differential magnetic field intensity. By using the differential magnetic field intensity, we can find total magnetic field intensity. So next, by using the relation between magnetic field intensity and magnetic flux density, we can find the magnetic flux density B bar. So our main purpose is to find B bar and H bar by using Biot Savart's law. So here first we are finding differential magnetic field intensity. By integrating the differential magnetic field intensity, we can find magnetic field intensity. Next, by using the relation between B bar and H bar, that means magnetic flux density and the magnetic field intensity relation, we can find the magnetic flux density B bar. So the Biot Savart's law, it states that the differential magnetic field intensity is directly proportional to the current element, inversely proportional to the square of the distance vector, and directly proportional to the sine of angle between current element and r bar vector. Here r is capital R, mistake, just modify it is capital R bar. So the differential magnetic field intensity directly proportional to the IDL, inversely proportional to the square of the distance vector, and directly proportional to the sine of angle between current element and distance vector. So next, dH bar equals to, we can also write dH bar directly proportional to IDL bar cross AR bar by R square. So we know that A bar cross B bar equals to modulus of A bar into modulus of B bar into sin theta, where theta is the angle difference between A comma B vectors. Here theta is the angle difference between current element and R bar vector. Here AR bar is R bar vector unit vector. So now apply A bar cross B bar. So DL bar cross AR bar equals to modulus of DL bar. It equals to DL modulus of AR bar. Modulus of AR bar equals to 1 into sin theta. So DL bar cross AR bar equals to DL into 1 into sin theta. Why? Because modulus of AR bar equals to 1. AR bar is unit vector magnitude always equals to 1. So DL into sin theta equals to DL bar cross AR bar. So next, DH bar equals to IDL bar cross R bar by R cube. So AR bar equals to R bar by modulus of R bar. So by using that equation, so we can write DH bar directly proportional to IDL bar cross R bar by R cube. So next, DH bar equals to some proportionality constant K into IDL bar cross R bar by R cube. So DH bar equals to IDL bar cross R bar divided by 4 pi R cube. Here K is proportionality constant and its value equals to 1 by 4 pi. So the total magnetic field intensity is H bar. So H bar equals to integral differential magnetic field intensity. So this is the differential magnetic field intensity equation. By integrating this equation, we can find the total magnetic field intensity. So next, by using the relation between B bar and H bar, we know that relation B bar equals to mu into H bar. So by using that relation, we can find the magnetic flux density B bar.